So for the warm-up, we're differentiating with respect to t. You all did this beautifully. dy dt equals 6x dx dt. So it's 6 times 2 times negative 5, which is negative 60. And every single group got it eventually, so well done. All right. Today is another day of applications. It's a fun day. Section 3.9, if you want to give it a simple name, you can call it related rates. Related rates. Today is the 7th. Today is October 7th. Already 1 week into October. All right. Now, don't write all this down yet. First, let's just talk for a minute. All right. So here's the thing. So if we are, suppose we're filling a balloon with air. Different things, characteristics of the balloon are changing, right? So as you pump air into a balloon, the volume of air in the balloon is changing. The surface area of the balloon is changing. The radius of the balloon is changing, right? So all these different things, say it's not a spherical, then the height, if it's different shape, might be changing, right? All these different things, dimensions are changing at the same time as we pump air into the balloon. Now, the rates of change of all these different aspects of the balloon are not the same, but they are related to each other. As the radius changes, the volume changes, right? As the radius changes, the surface area changes, right? They all are related. So numerically, the rates aren't going to be the same, but they relate to each other, right? So suppose I know how much air I'm pumping in because like my air pumper machine has some sort of like a gauge on it, right? So say I know the rate of change of the volume just by measuring how much air I'm pumping into the balloon. So however much air I pump in, that's the rate of change of the volume. If I want the rate of change of the radius of the balloon, then I can just use what's called related rates to calculate the rate of change of the radius without having to actually figure out how to measure the rate of change of the radius. So that's where related rates comes in. And you actually have already done one of these in your warm-up. Y was related to X. This is called a relation when you have an equation. So Y was related to X. So the rate of change of Y was related to the rate of change of X, right? They're not equal, but they're related to each other. So if I know the rate of change of X, I can compute the rate of change of Y. Okay. All of the rates today are going to be with respect to time, just so you know. Okay. So there's a procedure. So, and this is actually kind of important. So I do want you to follow these steps every time. I will follow these steps every time. And there's a reason I want you to follow these steps every time. Now, if you want to add a step 1/2, which is draw a picture, that's totally optional. That's up to you. No one's going to grade your picture. A lot of times the College Board will give you a picture, but so a picture doesn't have to be a required step, but if you like a picture, if you're real visual, then drawing a picture, you might want to have that as a step. Okay, but really, the first required step is to write down all the rates you're given and the rates you're trying to find. And I don't say this just as a help to you. I say these steps because these count for points. So when we are grading problems, you know how we break the problems apart? One of the things we're going to be looking for is, did you write out what each of your rates was? That will count for points. College Board also always counts this for points. Well, not always, but often. So one of the things they'll do in a related rates question is say you're given that the volume is changing at a rate of 5, cubic feet per hour. Then if you have a dV dt equals 5, you get a point. So it's like a free point for writing down your rates. So anyway, so write down your rates. Step 2, you need an equation that relates the variables. there's this little part here that says use secondary equations to eliminate any variables that do not have a rate listed in step 1. That's like fancy talk for saying that if you know the rates for x and y, or say you know the rate for x and you want the rate for y. So you have a rate for x and you have a rate for y listed with like a question mark or something. So anyway, so if you're interested in rates for x and y, then you don't want to write an equation that has an x and a y and a z, right? If you have an extra variable and you don't know those rates and you don't want those rates, you really shouldn't have it in your equation. So you got to figure out a way to get rid of it. All right, so in terms of the variables whose rates you have or want. Differentiate with respect to t, substitute your values that you're given, and solve. There are some gotchas. So I've written some cautions down there at the bottom. Caution number 1, do not forget product rule. Most of our equations are going to come from the wonderful world of geometry, right? Okay, yes, we love geometry, right? What did the acorn say in the spring? What? Geometry. Okay. See? Good, I got some laughing. Okay. Not even Bad Joke Wednesday. You got a bonus joke, right? Okay. So anyway, yeah, most of the equations come from geometry, and almost every single geometry equation, with the exception of like squares and cubes, you have multiple variables multiplied together, right? Area of a triangle, 1/2 base times height. Base is a variable, height is a variable, you're in product rule, right? So if you have any kind of variable times variable, you have to do product rule. And most geometrical equations have that, so got to do product rule. All right, don't forget units. That's just a given. You always have to make sure you put your units correctly, and we'll do units, talk about them as we go. All right, this last one, remember the signs of the rates are determined by whether the dimension is getting bigger or smaller, not a direction that it's going in. If you draw your triangle this way and say that's your x, and say like x is getting bigger, so like say this point is moving in this direction where x is getting bigger, don't say dx dt is negative because it's moving to the left, because if I drew my triangle this way, it's the exact same rate, and it's moving to the right, right? It has nothing to do with how, because it changes, if it changes just on how you drew your picture, it has nothing to do with it. It is the dimension getting bigger or smaller. If x is getting bigger, it's a positive rate. If x is getting smaller, it's a negative rate, regardless of direction. Okay? All right. All right. Everyone got the 4 steps written down? Good. All right. First problem is like an intro. This is like our gentle step into the real world of related rates. So, and then I'm going to talk to you for a minute. So the sides of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides are 15 centimeters long? So I'm going to draw a square. You don't have to draw a square. No one will grade your square. It's just for you. They didn't give us any variables. So you can pick any variable you want to represent the side of the square. What letter would you like to assign to the side of the square? A? Okay. Oh, you know, I'm all totally open to A, except we're doing area. Yeah, so I don't know if I want to use A and A. We could do big A and little a, but you want to do X? Okay. I'm just going to start simple with X. We can get more adventurous as we move on throughout the lesson. Okay. All right. So the side of our square is X. Now we've got our picture drawn. So the first required thing we have to do is write any rates that we're given and any rates that we're trying to find. So let's reread. the sides of the square, so the sides of the square, in other words, whoa. In other words, x, right? All right. X is increasing at a rate of 5. How do I write the rate of change of x with respect to time? dx dt. So the top is what's changing and the bottom is with respect to what? So I would write dx dt equals, and then what is it? 5. Is it, and don't put units now, like put the units at the end. So is it positive 5 or negative 5? Positive, how do you know? Increasing. Because the sides are increasing. Very good. Okay. All right. How fast is the area increasing? What are we trying to find? Okay, if you want to call area Y. I like to call area A. You can call area Y. I personally like to use Y for like other dimensions. But if you want to call it Y, you can call it Y. I'm going to call it A for area. So how fast is the area changing? So dA dt equals question mark. When the sides are 15 centimeters long. When what?
X equals 5.
When x equals 15. Okay. So we have two variables listed here, two rates. We have an x and we have an a. We need an equation that relates a and x. Move closer. Equals, yeah, you need an equation. You got to have two sides, right? So a equals x squared. Is everyone comfortable with that? Good. Now, little caution here. If you plug in your the dimensions you're given, first of all, is this square, like we say when x is 15, right? Is x always 15? Is the square just sitting there with a side length of 15 and it just stays static like that? No, it's changing, right? This is just, we want the rate at this moment that x is 15. So if I plug the 15 in at the beginning of the problem, so say I always plug my numbers in at the beginning into my equation, what will my rate always be? If I plug in my numbers at the beginning, what will all of my rates always be? They'll always be 0, right? If I plug in a 15 and then take the derivative of both sides, my rate of change in my area is going to be 0, which makes sense because I just said, hey, area is a constant, right? What's the rate that is changing it? 0, because it's not changing, it's a constant, right? You can't plug in constants at the beginning. You have to put them in at the end. There is an exception. The only exception is if you have a dimension that really is always the same, right? If you have something that truly is always constant, then you can plug in a constant for it at the beginning. But if it's something that changes, you can't plug in the number after you've differentiated. All right, so take a minute, differentiate this with respect to time. Please do not do logarithmic differentiation. What's the derivative of a? dA dt. What's the derivative of x squared?
2x dx.
2x dx dt. See how good you're getting at implicit differentiation? Did you get it? Oh, then you're good at it, right? All right, good. So now, now that you've differentiated, now you can plug in your numbers. So for this problem, what's x? 15. What's the x dt? 5. So our rate is 150. We need units. When you're doing the units, this is dA dt, right? 150 is dA dt. It's the units of A over the units of t. For this problem, what units is the area measured in? Centimeters squared. What's time measured in? Minutes. Centimeters squared per minute. All right. How are we feeling? Not bad, right? Good. All right. That was our intro problem. Now, the next problem is a very famous problem. This problem has been handed to students for centuries. For centuries, ladders have been leaning against walls and getting pulled away from the wall. So I did it when I was in high school. I'm sure that students, that took calculus 100 years ago did it when they were in school. It's the famous ladder against a wall problem. All right. So a 25-foot ladder is leaning against the wall. The bottom of the ladder is being pulled horizontally away from the wall at the constant rate of 3 feet per second. How fast is the top of the ladder falling when the bottom of the ladder is 15 feet from the wall? So personally, when I draw these, I draw a picture. I just draw the wall and the ground, and then I draw a ladder. To keep life simple, I'm just going to use x and y for my dimensions of my ground and wall. What I ask of you, and it's for no other reason than just for mercy on me, is if you use x and y, please let x be the horizontal and please let y be the vertical. All right? I can't, I could never label this y and this x. It would honestly make me not sleep at night. So I don't know how you guys could do it. Someone always does it. Please don't, because then my answer key has everything switched and I got to mentally reverse everything while I'm grading your paper. And what's the goal, right? When you're answering a question, make the grader happy, right? Right? Yeah. Okay. Always want the grader happy. Right, okay. Or indifferent, right? You want to not be noticed. Yeah, that's really the goal. Is to, just not be noticed. Okay, so I'm going to label this X and this Y. What do you want to call the ladder? Want to call the ladder Z? L?
Can we call it I like it.
I'm going to make all of you use my name for it. I'm going to call it 25. Now, why am I going to call the ladder 25? Because it's a 25-foot ladder and it's not changing ever, right? Don't give it a variable name if it's not changing. Okay. All right. So let's write what we're given. So the bottom of the ladder is being pulled this way at a rate of 3 feet per second. How would I write that as a differential in calculus notation? D what? D what? Dx dt equals 3, positive 3. How fast is the top of the ladder falling? What are we looking for? dy dt. Just so you know, if you want to know how fast this dot is moving, it's the rate that the dot is moving is the same as the rate of change of the dimension between the moving thing and a fixed object. So, I know when you're thinking, well, it's the dot that's moving at 3, it's not x that's moving. No, but this dimension is also changing at 3 feet per second. So if something's moving and you have a dimension between the moving thing and a stationary thing, the rate of change of the dimension is the same as the rate that the thing is moving. That gets a little, we get a little confused by that. So anyway, yeah. So dx dt is 3, dy dt is what we're trying to find. We need, and how fast is the tunnel? When the bottom of the ladder is 15 feet from the wall, so when x equals 15. There we go. I need an equation that relates the variables. You're going with trig? Okay. You're going to add an angle in here, a theta?
No.
Yeah. Don't introduce more variables because theta isn't fixed, right? If you put in a theta, theta is a changing quantity, and you don't know the rate of change of theta, right? Let's not. Okay. All right. But we are, just so you know, Ryan, that's actually coming up. So, good prediction. Yeah, I know. Okay. Rather than introducing a third variable, let's just stick with an equation that just relates x and y. So what equation have we got? Pythagorean theorem, right? It's a right triangle. Let's assume that the ground and the wall are perpendicular. So we have x squared plus y squared equals 25 squared. All right, take a second, differentiate both sides with respect to t. What's the derivative of x squared? 2x dx dt. What's the derivative of y squared?
2y
dy dt equals 2 times 25 d25 dt. Good. 0? Why is it just 0? Because it's a constant, right? Do you want to hear something funny? Do you want to know how tired first period is every morning? So I put that up, asked if anything was wrong. Nobody said a word, and we just kept on moving with that on the board. Right? Yeah. So they were, I know they knew it was wrong, but nobody wanted to take the stand and say something, right? So finally, there was one student who said, "Are you sure about that right side?" Anyway, you know what's funny though? Honestly, if I wrote that, d25 dt really is equal to 0 because it's the rate of change of the number 25, right? Which is 0 because it's not changing. Anyway, all right. Okay, so before we start, personally, before I plug in numbers, if there's something I can clean up, I usually clean it up first just to make the math easier. So I personally would divide both sides by 2 just, to make the math a little easier. All right, so now we start plugging in numbers, right? Once you take the derivative, you plug in the numbers. What's the x? 15. Do we know dx dt? 3 plus, don't know why. dy dt is what we're trying to find, so that's okay. This is where we write, and then we move on to the next problem, right? Not enough information, and then we just stop.
Oh, we can just Trying so hard.
Yeah, I wrote that down.
Wait, were you serious about the half information?
No.
Okay. I'm like,
Okay. No, of course we can figure out why. What's x? What's x? 15, right? There are two very easy ways to figure out y. One is you just wrote an equation that relates x and y, plug in your x and solve for y, right? Or you could be like a superstar and recognize that if this is 15 and this is 25, what does y have to be? 20, right? The 3, 4, 5 multiple?
oh.
Alright, so dy dt is negative 15 times 3 divided by 20. So let's do some canceling. I'm going to cancel a 5, make that a 3, make that a 4. So my final answer that I get is negative 9/4. I need units. What for what? What per second? Feet per second. Yes, because y is in feet and time is in seconds. Does it make sense that the rate is negative?
Yes.
Why? Because it's going down? It's direction?
It's decreasing.
Because y, the dimension of y is getting smaller. It wouldn't matter if like the top of the ladder stood still and the ground came up, right? It'd still be a negative rate because your y is getting smaller. Okay. All right. Good. One last little mention here about geometry that I didn't mention to you earlier. So, and I want this on the tape. Okay, is you are required to know all of your two-dimensional geometry formulas. So, we're talking like area, perimeter, circumference for square, rectangle, triangle, circle, trapezoid, all your major so circle and then triangles and quadrilaterals. We don't go any higher. We're not going to do pentagons or hexagons or anything, but you do need to know like square, rectangle, trapezoid, and triangles and circles, right? So if you come up to me during a test and you say, I don't remember the area of a circle, right? And you're going to end up with a 0 on that problem because you can't remember the area of the circle, I am going to look at you sympathetically with a nice smile, and I'm going to say, just do your best, right? And I won't have a lot of sympathy because you were warned in advance that you need to know the area of the circle, right? What's the area of the circle? Pi r squared. What's the circumference of a circle? Pi r. Good. Okay. So you have to know all your 2D formulas. Now, area of a trapezoid, 1/2 times the sum of the bases times the height. Okay. All right. The College Board tends to give you your 3D formulas, except for things like a box, right? They are not going to give you the volume of a box. They're going to expect that you know that it's length times width times height, right? So if you don't know that the volume of a box is length times width times height, now you know, right? Length times width times height. Okay. All right. But if it's like a cone or a cylinder or a pyramid or something like that, they usually give it to you. So they'll say, like, if it's a cone, they'll say after, like, they'll give you the problem, and then they'll have in parentheses, by the way, the volume of a cone is V equals 1/3 pi r squared h, right? And they'll give you the formula for it. We do the same thing. So if it's a 3-dimensional figure, we will usually give you the volume, or if it's surface area, we'll give you the surface area. But, you know, I mean, you're going to need to eventually learn those things someday just to get through life. So it'd be good if you knew for sphere, cone, especially if you go on to cut 3. Sphere, cone, cylinder, pyramid, if you know your formulas. There is one thing that they do require. One time, there was a problem where they gave you, it was a prism, and the base of the prism was like some squiggle shape. All right, and so like pretend this is like coming out like it's a prism. A prism is something where the cross sections are all the same, right, all the way through. So so they gave you the area of the base, and you had to figure out the volume, right? It was like that squiggle shape with a height. And if you knew area of a prism or volume of a prism is just area of the base times the height, you were fine. But if you didn't know volume of a prism is area of the base times the height, then you were kind of screwed. So you need to know that any kind of a prism, which includes cylinders and boxes, right, and anything, it's the shape, like whatever the shape of the base is times the height, that's the volume of your prism, right? Okay. So that came in handy one time in the AP exam. They didn't give that away, so you do need to know that. And really, just so you know, in case you're curious, anything that goes to a point is just 1/3 area of the base times the height, right? So if you have a cone or a pyramid, it's just 1/3 area of the base times the height. If you have a cylinder or a box, it's the area of the base times the height. The only thing that's really crazy is a sphere, right? So, but that one, I like the sphere because the 3's go together, right? 4/3 pi r cubed. I remember it's an r cubed, so there's a 3 on the bottom. So people tend to get confused. Is it a 4 or is it a 4/3? 4/3 goes with the cube. All right. That's enough of that little announcement. All right, that was part A. Let's do part B. At what rate is the area of the triangle formed by the wall, the ground, and the ladder changing when the bottom of the ladder is 15 feet from the wall? Now this is just a continuation. I'm only calling it, I'm only got it on a new screen just for space, right? You guys just keep on, it's just the same problem continued, right? Okay, so we still know our dx dt is 3. We now know dy dt is -9/4. We still have when x equals 15, right? I'm going to do a quick, there's our picture, x, y, 25. All right, so at what rate is the area of the triangle formed by the wall, the ground, and the ladder? So what are we looking for? The rate of change of the area. Yes? Oh, and sure, we could write y equals 20. Yeah, absolutely. Okay, good point. So what are we looking for? What rate of change? The rate of what? Area. So how would I write that in calculus notation? dA dt. Rate of change of the area. So up here with my given stuff, I'm going to write dA dt equals question mark. All right, so I know dx dt, I know dy dt, I want dA dt. I need an equation that relates a to x and y. Yeah, very good. Area of a triangle. Everyone agree? Are you okay? Okay. All right, find the derivative. Hey, Anthony, what rule are we going to have to use for this one? Product rule. He's very excited about it. Okay, what's the derivative of A? What? dA dt. When I have a coefficient with a product rule, I personally kind of think of this as being attached to the first variable. So I think of like my f as 1/2 x, and then my g would be the y, right? So f prime g plus f g prime. That's how I do it. You don't have to. Some people like to just take the half, put it in front, put a great big parenthesis, and just do x times y. And you get the same thing either way, right? Okay, so the derivative of 1/2 x is 1/2 times dx dt times y plus 1/2 x times, what's the derivative of y? dy dt. Good. Now we just plug in. So we have 1/2 times 3 times 20 plus 1/2 times 15 times -9/4. Just plug in all the numbers into the correct spots. All right, I'm going to clean it up. You don't have to. Technically, if this was an AP exam, you could leave this whole big thing as your answer with units. But I'm going to clean it up. So 1/2 of 20 is 10, so you get 30 minus 15 times 9, so 150, 135 over 8. 240 minus 135 is 105. 8. All right, we need units. What are the units for area? Feet squared. And then time is in what for this problem? Seconds. Feet squared per second. So the area is changing at a rate of 105/8 square feet per second. All right, think we're done with this problem? No. Of course we're not. All right, it's Ryan's time. All right, I'm going to redraw my triangle up here because the picture is kind of important for this one. So we have an X, we have a Y, we have a 25. All right, I'm going to rewrite my rates. dx dt equals 3, dy dt equals -9/4. All right, at what rate is the angle formed by the ladder and the ground? We need a variable for the angle. Theta. By the ladder and the ground, we're talking about that right there. Yes?
If you had like an example ABC on the exam and it was like this, would you have to draw a new picture and write the new?
Nobody cares about the picture, so they'll never grade a picture, but will you rewrite your rates? If it was 3 separate parts, which, I mean, it's rare that it would be that big of a related rates question. Usually related rates is like one part of every single topic you learn is like one part of a free response. So, I had to sneeze and now it's gone. So sorry. Oh, okay. Anyway, but if it was multiple parts, I would rewrite my rates every time. You can you can be messy. You can circle your rates and put an arrow. Like they're nice. Like if you've shown like bring this, copy this down. Like they'll take that, right? But I personally just would rewrite. It only takes a second. So anyway, all right. So what are we looking for in this problem? We're looking for the angle. It's right there.
The
rate of change of the angle. How do I write that? We're looking for d theta dt. When the bottom is 15 feet from the wall. So when x equals 15, whoops, I've lost, somehow I'm like losing parts of I'm going to write it up here. When x equals 15 and we know y equals 20. Okay. So we need an equation that relates the variables, and it's got to have a theta in it. Yeah, right.
Is it like tangent of theta equals x over y?
Okay, or y over x. But yeah, absolutely. Tan works. Any of the trig functions works. So here I'm going to give you some advice. So if you're watching the screencast, pay attention. I'm going to give you some advice. Whenever you get to pick your own trig function, always pick a function where, if you can, where there's a variable on top and a number on the bottom. Doesn't matter which one you pick, as long as you have a letter on top and a number on the bottom. So for this problem, you have 2 options, and they're both fine. So which function do you want me to go with? Sine. Okay. Oh, one really wanted cosine. You go with cosine. We'll get the same answer. Okay? All right, so I'm going to write Sine theta, what does sine theta equal? Y over 25. All right, sine theta equals y over 25. This goes forever. Whenever you have a number on the bottom, don't use quotient rule. It's not a quotient rule. When you have a number on the bottom, that's just a coefficient. Write it like this and you'll see it, right? So never do a quotient rule with a number on the bottom. It's always just, that's just a coefficient. You can just write it in front as a coefficient. All right, so we have sine theta equals 1/25 y. Take the derivative of both sides, please. What are we, let's see, is that a T? Okay, and so we're kind of close. Where is here? The derivative of sine theta is cosine theta times. Yes. All right, and then this is just y. It's 1/25 y. So we have 1/25. That would be if it was 1/25 plus y, but it's times, it's a coefficient. So it would be, like, what's the derivative of 5y? 5 times. Right? Yes. You got it. Good job. Good job. All right. Did I pause it? No, I didn't. Okay. All right. So the derivative of sine is what? Cosine. So the derivative of sine theta is cosine theta times what? D theta dt. If you don't have a d theta dt in your answer, how are you going to solve for it, right? So you have to have a d theta dt in your answer. Every time you differentiate with respect to t, you're going to have this differential for every single one of your variables. All right, so d theta dt equals, what is the derivative of 1/25 y? 1/25 dy dt. All right, so now let's plug in. Do you guys notice I never solve for what I want? I plug the numbers in first and then get it by. It's so much easier to solve with numbers than with variables. So, all right, so I want d theta dt. I need cosine theta. I know this is 1/25. I know dy dt is -9/4. I need the cosine of theta. Beautiful. Well done. Second period. All right. Very good. Okay, so guys, if you have side lengths on a triangle and you need trig values, don't try to find the angle, right? And then do an inverse trig on it. Just use the side lengths, right? If I want the cosine of this angle, it's adjacent over hypotenuse, 15/25. Just plug in side lengths for your trig values. So the cosine of theta is 15/25. Does everyone understand how we got that? You won't have a calculator. You're not going to be able to figure out this angle. If you come up to me and ask me and say, I don't have a calculator, how am I supposed to find the angle? Do you know what I'm going to do? I'm going to smile at you, and I'm going to say, just do your best, right? Okay. All right, so d theta dt equals 1/25 times -9/4 times 25/15. All right, let's cancel. Notice you never multiply and then cancel. You always just write all the numbers separately and then cancel first, and then you multiply, right? So kill the 25s, divide 25s, and a 3 can go All right. So we end up with a final answer of -3/20. I need units. All right, I'll give you a hint. Time is in seconds. I need units for theta. Calculus is always in radians. Always in radians. Even if we don't give you units like we didn't, it naturally falls out into radians. It's just all based on the fact that radians are a natural angle. It's in radians. So anyway, so yeah, -3/20 radians per second, which means this angle is getting smaller as the bottom of the ladder goes out. Does that make sense?
Yeah.
Yeah, okay. All right. Who needs a brain break? Okay, wait, let me pause. Okay. All right. A man who is 2 meters tall is walking away from a lamppost that is 4 meters tall. If the man walks at a constant rate of 1/2 meter per second, at what rate is the length of his shadow changing, and at what rate is the tip of his shadow moving along the ground? Now, through this problem, I wanted a shadow problem in my notes, and I didn't have one. And yesterday afternoon, I was going through my notes for today and realized, I don't have a shadow problem. So I typed this up real quick and just made up the numbers. And when we did it in first period, the numbers are like super easy and neat. So just know that not all shadow problems will have such nice numbers in them, but they're all the same method. It's just this one has really nice numbers. So anyway, okay. If we want, I could change it real quick to make it so the numbers are.
No, thank you.
Okay. Okay. All right. We want the man to be 8 meters tall. I don't think so.
Oh my gosh.
No, let's not have the man be taller than the lamppost. Okay. All right. All right. So anyway, so a man is, so I'm going to, while you guys are writing, I'm just going to draw a little picture here.
Oh, 2 meters. Wow. That's like
Oh, it's a lamppost of light. Oh, I get it.
meters.
Okay. All right.
Wow, I love this drawing.
Thank you. You know, I should have really majored in art, right? I know.
I think you would have made a big career.
All right. Okay, so this is my lamppost. This is my man. My man. When you need a shadow, the way that shadows work is you have your light source, and it's all of the light that is blocked from the thing that, the man, right? It creates that shadow. So what you do is you kind of go from your light source to like touch the top of his head and keep going down. And then I'm going to connect here the ground. So this distance right here, that's the shadow. That's his shadow. All right, we need some variables. So we need a variable for this length, and we're going to need a variable for this length. I don't care what letters. I will tell you, historically, I always just call them A and B, but you don't have to call them A and B. So what letters would you like to use? What letter would you like to use for the length of the shadow?
S.
S. S. All right. We're going to use S for shadow. And then we need this length of the distance between the man and the lamppost. And P, going with P. Postage stamp, sure. All right. Postscript, sure. All right. Okay. So we've got our letters. Now so we've drawn our picture. We've identified our variables. Let's start writing what we know. So the man walks at a constant rate of 1/2 meter per second, and he's walking away from the lamppost. So the man is walking this way. So what would I label as a half? What rate? Something is a half.
dp dt.
You say dp dt. Anyone say anything different? No? Okay, Faith is right. It's dp dt. All right. All right. Okay, dp dt. How do you know? Because when something is moving, the rate of change of the thing that's moving is the same as the rate of change of a dimension between the thing that's moving and a fixed object, right? The lamppost is standing still. The man is moving. So the rate of change of the man walking, which is 1/2 meter per second, is the same as the rate of change of the dimension p. Okay? Good. Very good. So dp dt is a half. We want, at what rate is the length of his shadow changing? What are we looking for? ds dt. Oh, there's this like block here. ds dt equals question mark. Okay. Oh, I didn't label a couple other things. So the man is 2 meters tall. Do I need to give that a variable?
No.
No, because he's probably not growing too much in this problem. All right. And then the lamppost is 4 meters tall, so I can just call that a 4. All right. So now we've written what we have, we've written what we're trying to find, we drew a picture. Now we need to write an equation that relates to variables.
Okay.
I gotta say, I was very, very impressed. There was a student in first period. First equation that was spoken was the correct one. And I honestly was in shock. Because once you know how to do these, they're super easy, but knowing how to do them the very first time is not easy. It's really tricky to recognize. Yes. Oh my gosh, I'm impressed again. Okay, do you guys hear Jennifer? Okay. I'm going to draw something. Don't draw this, you'll ruin your picture, okay? But I'm going to draw something here. So, we have a little triangle formed by the man in the shadow. And we have a big triangle, right, formed by the lamppost to the same point. These triangles both have right angles, right? And they both share a common angle right there, which means, therefore, these triangles are similar by the angle similarity postulate, right? Okay.
Yeah.
That was way too hard.
Okay.
Triple A.
All right.
Triple A.
Yeah. Never thought you'd use it again, right? Uh-huh. Okay. So, when we have similar triangles, their sides are proportional, right? There's a couple ways you can write the proportion. It truly doesn't matter how you write the proportion as long as it's mathematically correct. So Jennifer, since you came up with it, can you walk me through what proportion you would like to write for these? 4 over P plus S equals 2 over S. All right? So what she's saying is the big side of the big triangle to the big bottom of the big triangle is proportional to the same corresponding sides on the little triangle. All right, does everyone see that? Good. All right, before we differentiate, could we make our life easier and do a little cross multiplying?
Yeah.
Okay, let's do it. So we have 4S equals 2P plus 2S. Can I make it even a little bit easier?
Yeah.
Okay, so 2S equals 2P and S equals P. Only because I made the man 2 and the light 4. If I made the man 2 and the light 6, it'd be all different. But anyway, okay, so S equals P. We got to find the derivative of both sides with respect to T. Shouldn't be too hard. So what's the derivative of S? ds dt equals dp dt. And what is dp dt?
1/2.
1/2. Therefore, ds dt is also 1/2 meters per second. Don't think that they always work out to be equal. It's just because of the numbers I used in this problem. All right. That's part A. Okay, part B. Part B to the brain break. All right, so part B, at what rate is the tip of his shadow moving along the ground? So there's the tip. We want to know at what rate that dot is moving, which means what rate are we looking for? Okay, is it just ds dt? It's dp plus s dt. It's the rate of change of this whole thing, because it's got to be between the moving point and a fixed object. It can't be between moving and moving, because that's the shadow length anyway. So you got to do moving and fixed object. So I'm going to ask for a third letter here. Let's do this. Stop it. There we go. So frustrating. There we go. Okay. So I need a letter to represent the whole dimension. F. F for full. Okay. All right. So we're looking for part B, we're looking for df dt. I need an equation that relates to variables. Yes! Nailed it! The easiest equation. You don't have to pick a complicated one. If you've got one that's easy, go with it, right? So the easiest equation you can use is, I'm going to write it in red, F equals P plus S. Is it true?
Yeah.
Yeah. All right. df dt equals dp dt plus ds dt 1/2 plus 1/2. So df dt is 1 meter per second. Yeah, the numbers were really nice. Yeah. You will have shadow problems in your homework tonight, and you got to be careful because they can put the light source like from above going down or from on the ground going to a wall or wherever. Just remember, always draw your picture and remember, just think similar triangles. Every time for these problems, it's always a proportion of sides with similar triangles, all right? So it's just a matter of drawing the picture and then finding the similar triangles. Okay. Last one we're going to have time for today, and we do have time for it. This little image has come along every single, I don't know how to clear ink. There we go. It's gone. Okay. All right. A conical tank. A conical tank means it's a tank shaped like a what? A cone. Okay. Conical means cone shaped. Okay. Yes. Not comical, conical. Okay. Okay. A conical tank, vertex down, is 10 feet across the top and 12 feet deep. Now, here's the thing about 3D pictures. You can draw, cones are actually really easy to draw, right? You just draw a smushy circle and then 2 lines and you've got your cone. But for 3D, it actually, for your math, it's much easier if you just draw the cross section, not try to make it 3-dimensional. What shape is the cross section of a cone? Not this way, but this way. Triangles, right? It's a big triangle. So I know if you go this way, it's going to be circles, but we're going this way, it's going to be a big triangle. So just draw a big triangle. Don't try to make it 3 dimensions. It actually makes the problem harder. All right, so that's our cone if we were looking at it from the side. It is 10 feet across the top, and it is 12 feet deep. Now the cone is a tank. Let's pretend it's made out of metal, right? The cone is not changing size. It's a tank. So these dimensions don't change. All right. If water is flowing into the tank at a rate of 10 cubic feet per minute. All right. Sometimes it's not in your face obvious what dimension you're talking about, but let the units help you. What is measured in cubic feet? Volume. Volume. Area would be square feet. Volume is cubic feet, right? So 3 dimensions is volume. So they're saying water is flowing into the tank at a rate of 10 cubic feet per minute. So dV dt equals 10. When I talk about dV dt, am I talking about the rate of change of the volume of the tank or the rate of change of the volume of water in the tank?
Water in the tank.
Water in the tank. Do you all understand that? Okay. Because the tank doesn't change, but the water inside changes. Okay. And notice they use cones a lot because when you fill a cone, the water stays cone-shaped, right? So you get like little cone within a cone. Upside down. If you do it right side up, then it's really hard. But because you get that frustrum, right? But right upside down, it stays cone-shaped, which is nice. Okay. All right. Find the rate of change of the depth of the water when the water is 8 feet deep. I do not want to use D for depth. Instead, there's another letter that I want to use. I want to use H. Isham, was that you? Well done. All right. Why did you pick H? Because the formula for volume of a cone has H for height in it. I'm going to tell you. Volume of a cone is 1/3 pi r squared h, right? Okay, so it's best if you know a formula to just use the letters that are in the formula. So we're going to let h represent the height of the water in the tank. So we're looking for dh dt when h equals 8. Okay, so, we have a dV dt. We want a dH dt. Let's look at our equation. Do we have a problem? What's the problem? There's an R. We don't know anything about R. R is 5? Really? We're trying to find the rate of change of the volume of the tank? The R is a constant, stays 5 the whole time?
Yeah.
Really?
Yes, it's half of 10.
So this is the rate of change of the volume of the tank. I thought it was the rate of change of the volume of the water in the tank.
No.
Let's draw inside of this picture and label our variables appropriately, okay? Because this is water in the tank, not the tank itself. Tank itself isn't even changing, so you're right. If it was the tank, this would be a constant, this would be a constant, and dV dt would be 0 because the tank's not changing, right? Okay, but we're not talking about the tank. We're talking about water in the tank, right? Okay. So if I label R, that's the radius of the water, and H is the height of the water, and V is the volume of the water. Okay. Is R a constant? No. It changes as the water level goes up. The radius is changing. You can't just plug in a constant for it. Do you see anything? Want a hint?
Oh.
It's similar triangles again! Yay! All right. Now, be careful. They didn't give you the radius of the tank. They gave you the diameter, right? So make sure you're lining up with the correct numbers. So what number should I put up here for the radius? 5. All right. Ari, give me a proportion.
It would be R over 5.
Uh-huh.
equals h over 12.
Beautiful. Perfect. Well done. Does everyone understand how we got that?
Yeah.
Okay. All right. Solve for the letter you want to get rid of. So R equals 5/12 H. This is always true. This relationship is always true. No matter where you are in the tank, you'll always have similar triangles. They'll always have the same proportion. R is always going to equal 5/12 of H. Go up to your equation and replace your R with a 5/12 H. This is pretty much just, like as hard as it gets. There's actually more with related rates, but for this calculus class, this is pretty much as hard as it gets. All right. Before you do the don't do product rule. It's the same letter. Why don't we multiply them together first, right? Okay. So we get volume equals 1/3 pi times 5 squared over 12 squared. I don't know. Sometimes I like to multiply them out, and sometimes I like to just keep them, but that's okay. What would be my exponent on my h? H cubed, right? Okay. All right. So now find the derivative. What's this big giant thing in front? What is that? That's a coefficient, right? So that just comes along for the ride times the derivative of h cubed. What's the last thing? DH, good, Emma. DH, DT. DH, DT. All right, we are ready to plug in numbers. We know dV/dt is 10. Oh, you know what? Before I rewrite this, do you guys mind if I cancel the 3rd and the 3 here? Okay. So I have pi times 25 over 144. What's h? 8 squared. And dH dt is what we want to solve for. I have one caution with this. So I'm going to put what should be on top. 10 times 144 goes on top. Pi times 25 times 8 times 8 goes on the bottom. Let's clean it up a little bit. So, killing a 5, we get a 2 and a 5. We kill a 2 here and make that a 4. Let's see. 4 goes in here, 144, so 3, 24, 36 times, divide 4. I can kill off another 4, make that a 9, make that a 2. All right, so when all is said and done, my numbers that I get are 9 over 10 pi. One of the biggest mistakes students make is when pi is on the bottom. There is something about pi being on the bottom that students don't like, and a lot of students will put like 9/10 and then put like a pi over here. Guys, that's 9/10 pi. That's not 9 over 10 pi. You had better make sure that I know that your fraction bar goes over the pi. So make sure you're really clear. 9 over 10 pi. Okay. Units, I think our distance was measured in feet. Yep, and time was in minutes. So this would be what for what? Feet per minute, because it's the units of height over the units of time. All right, we did it. Just so you know, if you are bored, after you leave, I'm going to add one more problem to the screencast, which is when you have when you can't substitute out easily. Like here, we have volume and we have surface area, and they're both in terms of R. And the last thing I personally would ever want to do is solve this for R and plug it in here, because that would be a big pain in the butt. So I will show you how to do these separately and plug in after. Okay, just to finish up this last page of notes with no students in the room, just in case you want to see how to work this last problem. So the trick here, so the volume is increasing at a rate of 100, so dV dt equals 100. We're looking for ds dt, the rate of change of the surface area, when the diameter is 50. And of course, if the diameter is 50, that means the radius is 25. So the problem that we have is that volume is in terms of V and R, and surface area is in terms of V and R. Now, technically, you could solve one of these for R and replace your R in the other equation with what you get, but it's so complicated and ugly. So I strongly recommend instead that you just differentiate these both. Let's just see what happens. So if V is 4/3 pi r cubed, then dV dt equals 4 pi r squared dr dt. We know dV dt is 100, and we know our r is 25. So we can solve this for dr dt, and we get dr dt is 100 over 4 times pi times 25 times 25, and then we can cancel goodbye, 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 and our dr dt is 1 over 25 pi. Now we go to our S equation, and we do the same kind of thing. So ds dt would be 8 pi r dr dt, and now if we plug in 25 for our r, well, our dr dt, what is that? It's what we found. It's 1 over 25 pi. So canceling the 25s and the pi's, we end up with ds dt equals 8. And the units for surface area would be centimeters squared, and the units for time were in seconds, so it'd be 8 centimeters squared per second. That's it, guys.